In the previous video, we looked at deriving equations for a change in the robot's position in the global frame. So where is it at in this global frame? Changes in the global frame depend on changes with respect to that local frame, R. So we next looked at how do we derive those equations. How does our change in the x direction of our local frame, so that's the forward direction, how does that change depending on the rates, the angular rates of the two wheels? We also learned that we can't directly drive the robot in the local frame's y direction. There are some robots that we may talk about later in the semester called omnidirectional. That can drive in the direction orthogonal to the wheels themselves, but that's not what our differential drive robot is capable of doing. Instead, we can only drive forward, or we can rotate. Now we'll package those together into a kinematic model. Our kinematic model is a model of our WMR that governs how wheel speeds so that would be our values for phi dot map to WMR velocities. So that could be in our local frame. And I won't put the superscript on theta, or theta dot rather, because we learned that theta dot is the same thing, theta dot in the R frame is the same as theta dot in the G frame. We could also, if we prefer, have those quantities in the global frame. So that's for a kinematic model. For those that have heard the term before, I'll also give a definition for the dynamic model. That we can safely ignore until we start talking about simulation later in the semester. The big difference for a dynamic model is the key here is that the dynamic model will be more concerned with torques and accelerations instead of being concerned with velocities and speeds, which in this case is probably better put as velocity here as well, since we're talking about a signed value. So let's now define our kinematic state. And for this class, I will use the variable q for state. And you can think of this as a variable that keeps track of how our configuration changes over time. And so I'll mark our configuration as the x value, y value, and theta of our robot. If we cared to, we could also keep track of additional information. So q could be x, y, theta, and if it were important to know exactly the angle that the wheels are currently at, instead of the angular rate, we could also keep track of those two values too. That won't be important for our modeling for this class though. More important than this state vector is how this state vector changes over time. And we now have equations for those. And now is a good time to introduce the reference frame back into the equation. So let's say that we would like to know the state of our robot with respect to that global reference frame. Well, bringing that back over from our previous slides, we'll grab those equations. So here are the equations we want to grab. You can see I've got xg, y and g, and then theta dot. Let's clean this equation up a little bit. A more convenient way to write this is to take into account that we see XR and YR in multiple places here, and write this in a slightly more readable format. The format we'd like to use, I'll put an aside up here, looks something like this. We want our state and how it changes with respect to the global frame. We're going to have some transformation matrix, which takes us from the robot's reference frame to the global frame, and we'll multiply that by Q and the robot's reference frame. And remember, the idea here is that we want to cancel these R's out, so we're left with Q of G and Q of G, or Q dot of G rather. So given this format, we know that we're going to have two matrices, a transformation matrix and our Q in the reference frame. Writing down Q in the reference frame is an easier place to start. That's just equal to, with respect to the reference frame, x dot, y dot, and theta dot. And we can see that x dot is multiplied by cosine, y dot is multiplied by negative sine, and there is no theta dot as part of this first equation. So we can write this first component as cosine of theta minus sine of theta, or negative sine of theta rather, and 0. Likewise, the next row would be sine theta, cosine theta, and 0. In the final row, theta dot is just equal to theta dot, so there's no dependency on x dot or y dot, and we're just multiplying theta dot times 1 so that we can have this relationship here, theta dot equals theta dot. So now we have a slightly more common and compact representation of the equation Q dot in G is equal to some transformation matrix from R to G times Q dot in R. And now focusing on this equation, we can see after some quick cleanup here what the relationship between our input signals are, which directly impact x dot and theta dot, and how the robot actually moves in our two-dimensional plane and rotates in our two-dimensional plane. So to take this one final step, we could have x dot, y dot, theta dot all with respect to the global coordinate frame, and that's equal to cosine theta, negative sine theta, 0, multiplied by this frame in which we can substitute values in for theta dot and x dot. So let me grab those equations that we derived before. It would be this set of equations here. And we can substitute in our equations into this matrix here. And we're going to perform the same step. Since phi right appears in multiple places, and same with phi left, we'll break that into its own matrix. And what we'd really like to end up with is some 2x1 matrix with our two input values. These are our two control variables. After a sequence of transformations gives us our output, which is our state update vector, which I'll discuss more thoroughly in a couple of slides. So the question here is, what do we put in between these two? Well, if you remember your linear algebra class, you'll know that the dimensions need to match. So this is a 3x1 matrix. This one is a 3x3. And this one I told you was our two input values, so that's a 2x1 column vector. So knowing this, we know that the first dimension on our inner matrix here has to match the second dimension on this side, and likewise the second dimension of this one has to match the first here. So we know that the dimensions of this have to be 3 by 2. Essentially what we're trying to do is make it easier to pull out x dot r from here, which we know means we have to multiply by r over 2 times phi right. So that's an r over 2 here, and an r over 2 for phi left. Y dot is always 0, so we can multiply phi right and phi left by 0. Phi dot is multiplied by, theta dot is multiplied by phi right and phi left, which show up in our matrix here. Phi right is multiplied by r over d, and phi left is by negative r over d. So you can think of this matrix, the transformation matrix, as the frame transformation. So we have our output, which is the current state, or how the state changes rather. We have our input, and you could think of this as the physical characteristics. So that matrix performs a transformation from our input and turns it into how that input impacts our local change in position due to the wheel radius and the track width, the distance between the two wheels. So these two matrices together give us our speed and local coordinate frame. We then transform that to the global coordinate frame, looking at the current heading of our system. And this is a nice form for viewing our state and how the state changes over time, breaking it into these different matrices that have some sort of physical characteristics associated with them. So what do we do with this matrix here, the thing I keep calling the state output or state update equation? Well, before I tell you exactly what we're going to do with it, I want to motivate why we have it to begin with. Where we're going with this is that we will need to integrate we'll have to integrate our q dot, our state, over time. And that's because our WMR if you want the fancy word for it, is it's non-holonomic. What that effectively means is a value in the configuration space that a value in the configuration space does not map directly or one-to-one with a value in the task space. That's a really fancy way of saying that you could, over a certain amount of time, rotate, for example, rotate your right wheel and then rotate your left wheel. By A and B radians, and you'll get a different result. Than if you rotated them at the same time. Essentially, the history and the sequence of operations matter. So imagine the robot having commands where it goes straight and then turns. Sorry, goes straight and then turns and then goes straight again. You'll end up in a different position if your robot first turns and then goes straight and then, that's actually a bad example, first rotates, turns, and then goes straight again. And you would have the exact same final values for phi left and phi right. I'm not talking about the dot versions, just the final angles of the wheels themselves. So you could perform the exact same operations on each motor and end up in two different places depending on the sequence of how you commanded those motors to turn. There are more restricted systems where that's not the case. So for example, if I give myself a little box to write in, some examples of holonomic robots, or just systems in general, would include something like a robotic arm. The sequence actually does not matter. If you put one joint in the robot arm, so each of these joints will have different angles associated with them. If you put one joint at the robot arm at a certain angle, I'm just making up angles here, the sequence actually doesn't matter. You could do the first one and then the second one. You could do both at the exact same time. You could rotate this one entirely in the opposite direction and then back, but as long as it ends at 37 degrees and this one ends at 87 degrees, the robot will always end up in the same position in the task space, meaning this end effector will always end up at exactly this point in space. Another example of where this might happen, which is not exactly a robot, but similar, it's a similar system, would be something like a train. This is a more confined system, and you can imagine if I rotate the wheels on a train a certain number of rotations, it's always going to end up at a certain point. I could go forward, go backward, go forward again, but if the end result is that the number of radians carved out by the train is the same, it'll always end up in the exact same spot. Those would be two holonomic systems, meaning you wouldn't actually need to integrate over time. You only need to integrate over time if two final configurations can leave you in completely different places. The last thing that this set of slides will cover is something called forward kinematics, which is essentially this operation of integrating. So I introduced the concept of Q being our configuration, in the global space. Forward kinematics is the process by which we could now assign a specific time to each of these. So what is x at time t, for example? And this is a recurrence relation. So we would have that q of g at the next time step, we'll call it k here, just to follow standard notation, and because we typically use t in different places, non-discrete places, is equal to the integration over time. But since we're dealing with discrete systems, it'll actually be a summation. And you could think of it in two different ways. I like to think about it in this recurrence relation because it makes it easier to think about in terms of code later on. So at our next time step, it's just equal to where we were previously, plus whatever our change in Q is, times how long we were enacting that change in Q. So there's some slightly new notation here. All of our analysis of the actual motion of the robot dealt with these dots. Here instead I've introduced a delta and a delta time. The relationship between those is hopefully, if your time step is small enough, is that they're approximately equal. So you can take our equation from the previous slides and plug it in here. So how would that work? In code, you would just compute these 9 values. These are all constant values, and you would get these two values, phi dot right and phi dot left, from the encoders. And at some fixed frequency, so that would be at delta t, you would update this equation, and that would give us a new estimate of the pose. So your exercise for this week is to take these equations that I've shown here and implement them in code, and specifically C++ code that you can run on your microcontrollers. One final thing to mention is that later in the semester these equations will get a little bit more complicated. We'll perform something closer to localization, which is slightly different. Localization means that you have some idea of the map and landmarks around you. We'll also take into account imperfections. In both our sensors and our actuators. So currently, if we look at our global coordinate frame, our current equations would tell us if we started here and we knew our phi dot right and phi dot left, and we knew how long we traveled, we knew that at maybe the second time step. So this would be at time step k. At time step k plus 1, maybe we're right here. And again, maybe after performing some other maneuver, we've rotated slightly and gone forward, or maybe rather we've arced out a path to a third location. That would be at time step k plus 2. That's what our current model is telling us. When we start to take into account these imperfections, what we'll realize is that we don't know exactly where we are. Instead, we sort of have a general idea that we're somewhere within this bubble. And then over time, that bubble will get a little bit larger. until we see something. So for example, maybe there's some landmark here in the distance, and maybe our robot, the camera, can see it, and so it knows more precisely where it is, and we can shrink this bubble down. That's the process of localization. But that's for another semester. I just want to sort of foreshadow that, since it may be comforting to think that this equation is telling us exactly where we are in space. But due to slippages, numerical errors, and other factors, this equation here is always going to produce error that grows over time.